Equilibrium constant. Equilibrium constant is defined as the concentration of all the substances present at equilibrium raised to the power of number of moles they appear in the Stoichiometry equation. The product or the multiplication of the concentration of the products divided by the multiplication of the concentration of the reactant is defined as an equilibrium constant, provided the temperature remains constant. So equilibrium constant can be represented by Kc or Kp. Kc is essentially for aqueous solution and gases, Kp for gases only. And when the value of the equilibrium constant is low, the percentage U is low, as you can see from this graph. If the Kc-Kp value is low, it means that the main bulk of reactants did not chemically react. If it's about 1, then you'll be getting actually a reversible reaction. And if the Kc value or Kp value is very high, then it's likely to be an irreversible reaction because the percentage U of the product will be very high, so which means you get a lot of products and very few reactants are left. And bear in mind that unlike position of equilibrium, which is affected by many factors, chemical equilibrium is only affected by temperature. Let's take a look at how we develop Kc expression. So if given this as the equation, or this as the equation, this will be the Kc expression. Let's give some examples. In this reaction, you find that there is the Kc expression, and the unit of Kc will be respectively as such. Similarly, in the case of this reaction, you will find that there is the Kc expression, and then you will get the Kc unit as such as well, Kp. For the case of Kp, as we probably already realized, that based on the ideal gas equation, the partial pressure is actually directly proportional to the concentration, provided the temperature is constant. So in this case, if this was the equation that we're looking at, then the Kp expression will be the partial pressure of your product, which is your SO3, divided by the partial pressure of oxygen, and partial pressure of the sulfur dioxide raised to the power of 2. Remember to take note that you need to raise to the stoichiometric constant. The unit will be in Pascal -1. The next part is that we're going to explain why when you add more solid reactants or solid products, or you remove them, it does not affect the position of equilibrium. The reason is because when you look at the Kc expression, for example, if you look at this equation, this will be the Kc expression. However, we need to note that both calcium oxide and your calcium carbonate are both solid. So what does concentration of a solid means? Concentration of a solid actually is equivalent to its density. And we need to bear in mind that density will always be constant, regardless whether you have 1 gram of iron or you have 5 tons of iron. The density is still the same. The 1 gram of iron will sink like the 5 tons of iron in water. Therefore, because of this, what it means is that these two values now becomes actually a constant value. Because they're both constant value, we can now shift them over together with the Kc to come up with the new equilibrium constant Kc prime, which is only solely expressed in terms of the concentration of the gas. So in this example that we illustrated, you will find that if you were to add calcium oxide or you were to add calcium carbonate, the concentration of your CO2 at equilibrium remains unchanged. And therefore, because of that, the Kc, the equilibrium constant remains unchanged, so there will be no change in position of equilibrium. So hence, in conclusion, when you actually have any solids, all right, when you have any solids and you determine and you are working out your Kc and Kp expression, you do not include them. Water. In the case of water, when expressing Kc expression, it is less clear. You will find that in this example that's illustrated here, in the production of your ester, the water is included. The reason is because water is limited. In this reaction, they're taking pure ethanol to react with ethanoic acid, pure ethanoic acid, and then you produce your ester and your water. So the total volume of the liquid, in the reaction mixture is in actual fact the volume of your alcohol, your acid, your ester, and your water. Everything all aggregated together. So in this case, the concentration of water will be given as such, which means that when you produce more alcohol, more ethanoic acid, or more ester, it will actually affect its concentration. Hence, because of this, you will find that in the Kc expression, you need to actually include the concentration of water inside. Conversely, in exactly the same equation, what we have is that you have excess water. So in this example, we could have 100 cm³ of your aqueous ethanol added together with 100 cm³ of your aqueous ethanoic acid, which means that in total, there will be approximately about 200 grams of water in the solution. In this case, we need to bear in mind that because the volume of water is significantly larger than the volume of your alcohol, acid, and ester, it means the total volume now is approximated as the volume of water. Therefore, if you were to work out the concentration of your water, it is the number of moles of water divided by the volume of water, and that means it is its density. If the reactions were to move forward or move backward, when you produce more or less water, you will find that with more or less water, the concentration of your water is still its density, which means it is a constant value. Hence, because of this, the Kc expressions that is derived will omit water now, and therefore the Kc prime will actually be of this expression, and more importantly, the unit of Kc will actually be mole minus 1 dm3. And like in this example here, there will be no unit of Kc. We'll now take a look at this example. In this example, what we have is we have SF4 reacting with fluorine to give this all in gaseous state. So therefore, this is the Kp expression, this is the Kc expression. Let's discuss now what happened if we decide to decrease the volume of the vessel. If you decide to decrease the volume of the vessel, it will favor fewer gaseous molecule, so the position equilibrium will shift forward. And let's now take a look in terms of the Kc expression. From the Kc expression, we can take the number of moles of SF6 divided by the volume of the vessel. Similarly, SF4 divided by the number of moles of volume, and NF and fluorine divided by the volume of the vessel. And you will end up with this expression as such. And so in this example that we illustrate, it is quite clear that the volume of the vessel drops. So when the volume of the vessel drops, you will find that now it will actually change the value of the Kc, which should not change because, as highlighted earlier, the value of Kc and Kp can only be changed when the temperature changes. So in order for the Kc value to be restored to its original value, you will find that if this number is actually dropping, it means that the numbers in the denominator must also drop, while the numbers in the numerator must increase, which means you need your n number of moles of SF6 to increase, number of moles of SF4 to decrease, number of moles of F2 to decrease. To do that, you obviously support the fact that the position of equilibrium has to shift forward, because when you shift forward, number of moles of SF6 increase, number of moles of fluorine drop, and number of moles of SF4 drop. This further reinforces the fact that the Kc and Kp expression are in line with actually the Le Chatelier principle. Let's study now what happens when the temperature increases. So given that the reaction is exothermic, when the temperature increases, it favors endothermic, which means position equilibrium ought to shift left. If it shift left, so does the Kc or Kp increases. Let's take a look. If you shift left, then the denominator will increase, the numerator will drop. Therefore, because of this, the Kp value or the Kc value will drop. Hence, one need to bear in mind that when temperature changes, it is important to analyze and check whether the Kc or Kp value decreases or increases. And similarly, in all cases, if the position of equilibrium shift left, you end up with more reactant. More reactant means Kc, Kp drop. However, if a certain reaction allows the position of equilibrium to shift forward, then you get more product. If you get more product, then the Kc and Kp will increase. Let's take a look at what happened if we study this reaction. And we are going to introduce a change, which is to add helium gas as an inert gas at constant volume. So the first thing to note is that when you add helium gas as a constant volume, one need to know that the partial pressure of each of the gas does not change. However, the total pressure in the vessel increases because now you have an additional gas component, helium. However, it is important to note that if you look at the Kp expression, since the partial pressure of SO2 and H2S does not change, then certainly there won't be a change in the position of equilibrium. Therefore, it is important not to be mixed up by the fact that you will conclude to say that if the total pressure increase, then it will favor fewer gaseous molecule. That will be incorrect as an analysis. It's important to check that if position of equilibrium need to alter, then the partial pressure of SO2 and H2S must change. But in this case, when helium gas is added at constant volume, both the partial pressure of the gases do not change. Therefore, there's no shift in position of equilibrium. Now let's take a look when we decide to add helium gas at constant pressure. When you do that, it is quite similar to that of putting a gas in a balloon. Because when you put more gas in the balloon, the volume of the vessel will increase. So that is in fact the change rather. So the important thing is to link it to the fact that the volume of the vessel increases. When the volume of the vessel increases, it will favor more gaseous molecules. And because the volume of the gases increases in favor of more gaseous molecules, position equilibrium will shift left. And another way to explain it is to look at the Kc expression. Substituting the concentration of sulfur with its number of moles divided by volume, and similarly for the case of H2S with the volume, you will end up with this expression. So with that, we clearly know that if the volume of the vessel increases, which means the numerator increases, then we definitely need the denominator to increase as well. So that is in line with what we analyze in terms of position equilibrium, because if it does shift left, then both H2S and SO2 increase in its number of molecules. Hence, because of that, we will conclude to say position equilibrium shift left, despite the fact that the total pressure remains constant.